Hello and welcome back to Physics for the 21st Century. Again, my name is Greg Perugini and I will be your guide through this topic as well, the laws of motion. So let's get on with it. And up to now, we haven't really been looking at the thought of what is causing motion to happen, whether it be kinematics in one dimension or in two dimensions, where you break the vectors into their components. We haven't really been looking at what causes that motion to happen. What causes the velocity to go from 0 to 50 meters per second, for instance. Force is related in Newton's equations by mass and acceleration. So these were formulated by Sir Isaac Newton in the mid 1600s. And we think of forces in everyday experience as pushing an object around or throwing or kicking a ball, for instance. But forces may not be able to move an object. In Newton's definition, forces cause an acceleration. And they can be contact or field forces. The fundamental forces that we have are gravitation, of course, gravity. If we look at the acceleration here, that acceleration can be gravity, negative 9.8 meters per second squared. We could have electromagnetic force. Nuclear force is the force between subatomic particles, and there's a weak force by radioactive decay. Right now, we're looking at force that I would give by contact or through a field gravitationally. What we must remember here is that forces are vectors, so we can do the vector algebra with them. They can be added. Forces can negate each other. If I'm standing on the ground here, there is a force of gravity down, right? Based on my mass, if I am 100 kilograms, and gravity, negative 9.8. That is the force in what we can call weight. And that is pushing me down. But am I accelerating down through the ground? No. Why? Because there is a normal force if you like, the force of the earth pushing against me. Hence, I am in an equilibrium. So, forces as a vector, and we write normal force like that, can oppose each other and negate each other. We can have friction, which may hold an object as I try to push an object. Say I have an object here. I'm trying to push this object. In a frictional force, we'll talk about that in another topic, is holding this in place. And it's more frictional force than me pressing on it. Then I'm not going to be able to move the object. In a sense, it will be in a static equilibrium. My force negated by the frictional force. So the laws of motion, if we can look at them in detail here, we talk about the first law being the law of inertia. What's in motion tends to stay in motion. What's at rest tends to stay at rest. There are several definitions for each of these, but that's probably the one that you can relate to best. It is a little bit different from common sense in the sense that I throw something and I know it's going to stop. Why? Because there's a force of friction. There's air friction and there's the force of gravity actually going to pull it down to the ground. But if we talk strictly without those forces, when I start something moving, there has to be something to either slow it down or reverse it or go against it to make it go off course. There has to be a force of some type that pushes it aside. And that brings us to our second law of motion. That in order to have that happen, to have an acceleration on any mass, I need a force. Otherwise, if I throw an object at a velocity of 30 meters per second in this direction, if there is no air friction, it will keep going forever. If there's no friction at all, it will keep going forever. The Voyager spacecraft is outside our solar system now. It was launched in 1977, and it is still going. It has no more rocket fuel, but there's nothing, or I should say very little, in empty space to slow it down. So it will continue at many thousand kilometers per second, and continue that until something stops it. And it could be many, many, many centuries for that to happen. So that's the second law as it relates to the first law. Now the third law says forces come in pairs. If I press on a wall, the wall is going to press back on me. There is no force that comes without its equivalent pair. You see this with rockets, right? In space, a rocket can fire its engine. It fires back. The rocket moves forward. In a sense, that is how we walk. We press backwards with our feet to go forward. If there was no friction on the ground to allow us to press backward, we would just imagine trying to walk on a super slippery surface like ice or whatever. You have nothing to push back against. You cannot go forward. So we can have two types of equilibriums. The equilibrium where I'm standing on the ground and I am not moving. All forces are balanced. I am at rest. I'm not pressing in one direction or walking in one direction. The force of gravity is pressing down. The normal force of the earth is pressing up. And then there's the dynamic equilibrium of constant acceleration, where the kinematics can come in play. In fact, let's look at that. I'll put them kinematics right back up here like we had before. Because if we have F equal ma as Newton's second law, you could see easily how it relates to the kinematics if we have a constant acceleration, right? The kinematic equations, for them to work, need a constant acceleration. Well, this acceleration is no different than any of these. It is a vector. I can put the little vector sign above it. And force is a vector. So I could have various forces at various directions and use the kinematics to solve them by breaking them into their components, as we've done before, right? Vector algebra. Let's take an example. I have a tube. And this tube is 0.9 meters long. And I have an object here in this tube. It's 3 kilograms. It's the start of that tube. I want it at the end of the tube to be going at 50 meters per second. How much force do I need? So this isn't as straightforward as we've seen the other examples, perhaps. I mean, this isn't just plug and chug, as they say. I don't give you the acceleration, 2 of these 3 variables, and you solve for the third. We don't know what force is. That's what we're trying to solve for. We know what mass is. That's 3. But we don't know what acceleration is. However, what do we know? Velocity initial, 0. Velocity final, 50. Change in distance, 0.9. And that it would have a constant acceleration through this tube is not too much of a stretch, right? So given that, we can look at our kinematic equations. In this one particularly, this last one here, I can use this because I know the velocity final is 50, so we'll do 50 squared. Velocity initial is 0, 0 squared, 2 a 0.9. So just like we did the vector algebra before and the kinematics before in 1 dimension and 2 dimension, this is just simple 1 dimension kinematics. Solve for acceleration. Acceleration in this case is 1400 meters per second squared. So now we have that second variable for this equation, right? 1400. And hence we can solve F equal ma, F equal 3 times 1400. That's going to give us the force we need to create the acceleration necessary over this distance to reach a velocity of 50 meters per second. And you can do that calculation, but it's fairly easy math. 4,200 newtons. That's the unit for force, newtons. And again, it is a vector. It's a vector. Okay. So, given that I have a normal force that presses down, and if I press down, I create an equilibrium situation, but the normal force would press back up of that equal amount. For instance, let's go back to just a very simple example. If I press down with 50 newtons of force at 40 degrees on an object that is 5 kilograms. What does this mean? If it's not moving, it's assumed that there is frictional force that will not allow this to move. I have created not just the normal. If I wasn't pressing on this at all, what would the force be? There would be a force of gravity 5 times 9.8. But since I'm pressing on it, there is the summation of all the forces, five times 9.8 plus this force, or I should say the component of that force, in the y direction, downward, would be 50 newtons times sine of 40. That would be the force downward for this scenario. I am pressing down and gravity is pushing down as well. So the normal force would be going up the positive of this. Otherwise, if it wasn't, right, this would be going through the floor, right? We have an equilibrium situation where the Earth is going to press back the combination of what we press down plus what gravity's pressing down. So, in conclusion, remember to break forces into their components when necessary. F equals ma in all directions. It's a vector, and the acceleration is a vector. But make sure you don't mix apples and oranges together here. If you have an acceleration in the y direction, you could calculate the force in the y direction separately and from the other component, which is force in the x direction with acceleration in the x direction. Force and acceleration are vectors. And you can use kinematics to solve for acceleration in any or all directions using the kinematic equations. So that should be what you need and all you need for the laws of motion and working through the laws of motion. In a subsequent topic, we're going to be working with force in terms of friction. And we'll get to that next topic.